Hey guys, EJ Williams here. I wanted to go over what we covered in class last week with a design problem for a lithium battery pack design. We talked about series cells, parallel cells, and how to come up with how many series cells you need and how many parallel cells you need for a certain application. Our application we did about the size of a go-kart, which is what we are training for, right? We're racing electric go-karts around Purdue University's track. So let's go ahead and dive into it. Before we can, well, let me say this first. In order to design, we're going to have power that we're designing for, and then we're going to have energy that we're designing for. Those are the two aspects. And there's also physical designs, but we're not going to cover that right now. That's, weight, volume, how to fit it on the cart. But we're just going to talk about power and energy. So our electric go-karts, we are going to take about, we're going to start with this assumption. It takes about 50 watt hours to go around the track once. And we're going to say that this is a 50 lap race. Okay. So what does that equal? That equals 2,500 watt hours. I don't know if it's capital H, lowercase h. So that's the amount of energy that we're going to assume we need. Now, obviously, this is a very rough number. It could be between 40 and 80 as what I've seen throughout the years, but we're just designed at 2.5 and kilowatt hours, and we'll go from there. Don't forget this equals 2.5 kilowatt hours. So this is that was pretty easy. That was the amount of energy that we think that we are going to need in order to finish this race. But we got to dig into that because there's actually some more aspects to it. But that's the right ballpark. So now the question is, we're going to use 18650 cylindrical cells. We don't use pouch cells in vehicle applications. Pouch cells are more for your handheld electronics, mostly because they expand. And it's hard to make bigger battery packs with pouch cells, but when you're making a big battery pack, you're going to use the more cylindrical type. So we're going to use the 18650 cell type. So it's the most popular. If you go online, when we went over this in class, we actually pulled up the real data sheets for cells like Samsung's INR650. We also did a Panasonic cell, but there's a ton of cells out there, and you look at the data sheet. And now that we're talking about cells, let's realize that there's two types of cells out there. There are energy cells and there are power cells. Obviously, the energy cells are more about giving a lot of energy in one single cell, and the power cells, here are my notes from class, sorry. The power cells are the ones that, they may not have as much energy, but they're really good at giving out their energy over time, aka power. So those are power cells. We're going to just choose an 18650 and we're going to design for it and see if it worked. I think in our notes we chose let's see. Well, let me just start in theory. Most 18650s are 2 amp hour. Okay, so let's roughly say 2 amp hour is your energy or capacity, I guess you would say, in an 18650. Let me touch on that. Energy, capacity, and voltage. Energy is measured in watt hours. That equals current, which is measured in amp hours, because we're talking about amounts, capacities. We're not talking about actual current in amps. And then multiplied by voltage. So, and obviously that would be volts. So you've got this right here. Whenever we talk about energy, we're going to be talking watts or watt hours. Watts is power, watt hours is energy. And then this right here is actually considered the capacity. I know when you guys are probably more used to seeing amp hours or milliamp hours when you're buying your electronics battery packs. And that is because it just assumed anything USB is 5 volts. So if you hold this at 5 volts, you can talk about this all the time and have it be equivalent. But I think it's pretty ridiculous that people measure these battery packs for phones, portable battery packs for phones in amp hours, because that's not a true measurement of energy. You should be talking about watt hours. But once again, you can do it in electronics, USB electronics, because you're holding it a constant 5. But if you're really talking about true amount of energy, we got to be talking about watt hours. And the difference is obviously the voltage, right? So if you've got a 20 amp hour pack at 5 volts, that's much less energy than a 20 amp hour pack at 80 volts. We're talking lots of different energies. The 80 volt 20 amp hour pack can, push you around a go-kart track for 50 laps, when a 20 amp hour 5 volt pack could probably only do half a lap. In reality, it's not that much energy. It's just enough to recharge your phone. So that's your energy versus capacity versus voltage. So I wanted to cover that. Well, let's talk about cells. So we know that we're trying to get this much energy. Okay. So let me tell you, most cells are 2 amp hour and they're always 3.7 volts, right? So I guess a side note on lithium 18650s, on the high end, they will be 4.2 volts. On the low end, they'll be 2.8. And this can vary a little bit, but when you're talking about lithium, not lithium iron phosphate, that's a little different. But when you're talking about lithium ion chemistries, you're usually going to be fully charged 4.2 volts per cell, and then 2.8 volts per cell on the low end, with a nominal voltage. This is called the nominal voltage right here at 3.7. So if you want to talk about the energy that is here, you just take 2 times 3.7 equals, what is that? That's my equal sign, apologies. 7.4 watt hours. So this is how much is in one cell right here. So quick division, let me get my phone is recording. Quick division of 2,500 watt hours divided by 7.4. All right, I went and grabbed a calculator, and we found out, so for 2.5 kilowatt hours with 7.4 watt hours a piece in each cell, you would need 338 cells in order to get to this energy level. But let's review again. I said this isn't really the energy level that you want, because this would assume that you're crossing the finish line with 0 energy in your tank. Now, that may work for gas cars, and that may be the ideal way to win a gas race, because the last drop of fuel, you can still have the same amount of power. But the issue with lithium is when you get to the lower state of charges, 30% energy left in your pack, 25%, 20% energy left in your pack, you're down on the lower end of your total pack voltage. And you can't, because of voltage sag, because of when you pull current from that pack, it will reduce the pack voltage to the point where you're actually bottoming out the pack voltage or taking it below the minimum pack voltage because of all the current you're pulling through it. So let me say it another direction. If you were pulling instead of pulling, 300 amps from a 72 volt pack, if you were just pulling 1 amp, you could easily take it down to 0% state of charge and maintain 1 amp the whole time, no problem. But pulling 300 amps from a pack, when you get to your lower states of charge, it won't be able to give you the full 300 amps near the end of its state of charge. So if you want to keep your full power, you have to have more energy on board your cart in order to maintain 300 amps. Meaning, when you cross a finish line, you actually want to be at like 30%, maybe 40% state of charge energy left in the pack. So let's just, I know from practice, 2,500, let's say it's like 3.2 kilowatt hours is the ideal. So rather than 2,500, we're going to do 3,200 watt hours to finish race, or to be competitive in the race. So that's our new metric. Now we're going to do 3,200 divided by 7.4 watt hours per cell And we have, put that in the calculator, 433 roughly cells is how many cells we are going to design for that are 2 amp, 3.7 volts. But one interesting, this will probably get us actually to the ideal. Let's play this out. I hate that we're not using an actual data sheet here. We're just assuming these numbers. And actually, now that I say it, we can't assume these numbers because there's another assumption, and we have to know the power. We know the capacity / energy of this cell. Here's the energy of the cell. We know the voltage of the cell, but we don't know the ability of this cell to give out its energy, meaning its power rating. We don't know this cell's power rating. Power ratings, and this is very important, are measured in C. We call it the C rating. And if you're going to start talking about EVs and you want to be an EV enthusiast or an EV engineer and you want to know what you're talking about, you're going to have to bring up C rating. I mean, this is key vocabulary. And what the C rating of a battery is it is the amps drawn from a cell or a pack divided by, sorry, that's drawn right there, divided by amp hours of the pack. All right. So if we pull, let's take like one cell, right? So we know that one cell is 2 amp hour. And if let's say we pull 4 amps from it. So 4 amps from a 2 amp hour cell, that equals 2C, meaning you are pulling this cell, at 4 amps, you're pulling it at a rate of 2C, right? Now another example real quickly, let's do 10 amps. Sorry, I get that up there. From the cell, same cell, 2.2 amp hours, that equals 5C. So what that means is the higher the C that you're pulling it, the more amps you're pulling from the same size cell. It may be obvious, but there's only so many amps that a 2 amp hour cell can give. There's only so many amps that a 1 amp hour, there's only so many amps that a 10 amp hour cell can give. And when you divide them out, you get a C rating. Now in application, this is the difference behind pulling 1 amp from a AA battery, which would probably max it out, and pulling 1 amp from a Tesla battery, right? So pulling 1 amp, I don't know what a AA battery is, but let's just say it's 1 amp hour, 1 amp divided by 1 amp hour, that's 1C. So you're pulling 1C from a AA battery, but actually I bet a AA battery isn't even 1 amp hour. I bet it's like 0.5, which in case it's 2C. Anyway, you're getting a significant pull just for 1 little amp. You're pulling a decent amount from a little battery, a AA battery. But now let's say the Tesla. I don't know the Tesla amp hours, but I do know the Tesla is about, we'll say 90,000 watt hours. And we know that it is 330 volts. And the math right there is divided by 330 is about 272 amp hour. So the Tesla battery is 330 volts, 272 amp hour roughly. At least that's what it was when I worked there 8 years ago. Now, if you pull, this will be crazy. If you pull 1 amp from a Tesla battery of 272 amp hour, 1 over 272, 1 over 272 is 0.00, we'll just say 4. 0.004C, meaning that's nothing. And we know that 1 amp from a Tesla battery is nothing. And your C rating shows it. It's nothing. You're not pulling much at all. It's not hurting the battery. It's not abusing the battery. It's very little from the battery. But pulling 1 amp from a AA battery is 1 full C or 2 full C. So that's where C ratings come into play. And basically, another way to say it, it is the amps divided by the size of the battery, because when you're drawing amps, you need to know, am I drawing from a big battery or am I drawing it from a little battery? So anyway, that's how you talk about a C rating. C ratings are very important because that is how a cell data sheet will tell you it how powerful, how okay it is with giving out its current. I will say most cells, energy cells can do like 3C roughly continuous. Remember, energy cells can do 3C roughly. Power cells can do 10 to 20C continuous. But, energy cells are like 3.2 amp hour, and these are like 2 amp hour. So you got to, pick what you want your cell to be better at. Do you want it to be better at C rating, or do you want it to be better at amp hour capacity? And the application difference is more like, this could be like a small non-racing RC car. Well, most RC cars are racing. Golf cart. How about that? Golf carts are not meant to be very powerful. So, golf cart applications could have high energy, but then power applications are going to be like drones, where you want very, very high power for little space and little weight. So that's the difference between the two, between an energy cell and a power cell. Power being C rating, energy being the amp hours or the watt hours, the total watt hours on board the cell. So now let's take an example of, well, here's what we do actually. We know how many cells we want. We decided we want 433 cells in this pack in order to get us 3.2 kilowatt hours. Perfect. Now, in terms of voltage, picking a voltage is, in our case, a 48 volt is not necessarily inferior to a 72 volt. I will mention real quickly what's called I squared R losses. In theory, not really an application. In theory, this is important because what it means is current is extremely more important than the resistance of a wire. And we're talking about power loss through a wire. So, those cables that carry the current, what's the power loss? And by the way, the power loss becomes heat. So if you've got a small wire, high resistance, and you've got a high current, you're going to be having high power losses. Well, those power comes out in heat, and therefore could heat up the cable and melt the insulation. That's literally how a motor will burn out. It's got windings inside that gets higher current than it wants, and then it heats up and then melts the insulation. Well, anyway, we're talking the big fat wires on the go-kart, and the resistance is so low, it's kind of minimal. But this is the reason why. I guess let me make another connection for you guys. Ohm's law, V equals IR. So if another way to look at this is, PIV, power equals current times voltage. Then you supplement the two, and that's where you get the power losses is equal to I squared R. So that's why it's called I squared R losses. Where am I going with this? That's in theory why you would want to reduce current in order to have smaller current, but in order to have the same amount of power, but smaller current, you increase the voltage. This is why transmission lines for your power grid are very, 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 very high voltage, because they are going really far distances. Even if they have low resistance, they're going such far distances that this R will eventually add up. So they want to make current, which by the way is way more important than resistance due to this squared. They want to make this as small as possible, which is why power transmission will make the voltage as high as possible so that the current here can be as low as possible. So that's in theory why you would technically want a higher voltage, but we're talking 48 volts to 72 volts with an R that's so low it doesn't matter. We're not doing transmission, we're just going through 3 feet of cable. So in theory it doesn't really matter, or in theory it matters. In application, our application, it doesn't matter. So you would usually choose something around 48 volts to something around 72 volts. But the fact that we're saying the word 48 or 72, this is archaic. This is based on 12 volt intervals because of 12 volt lead acid batteries. We don't talk like this anymore. When you're in lithium, you say series cells. So you stack, where was our, a cell is 3.7 volts nominal. If you're talking full pack voltage or under pack voltage, you do the same. So 3.7, we'll just say 14. Let's say, for example, 14S, S being series. Well, that means 14 times 3.7. I'm going to give you that exactly. 14 times 3.7 is 51.8 volts. So we're not truly a 48 volt pack. We're actually a 51.8 volt pack nominal. because lithium is not in intervals of 12. But you don't really say, you can say nominal pack voltage, but if you really want to sound like you know what you're doing, you say, oh, this is a 14S pack. Because anyone that's listening to you and smart enough will know, oh, we'll just take 14 times 3.7 and you can get the pack voltage. So this is more descriptive than this. So we talk in series cells whenever we're talking about pack configurations. Now we need to know, do we want to go 14S for our battery pack with how many cells? 433 cells. Or do we want to go higher than this? Higher than this will get more towards like a 72. Well, let's just say like 20S. Let's see what 20S looks like. 20 times 3.7 is equal to, what is that, like 74? Let me just make sure real quickly. I should know this, but I am graduated and don't do math very often anymore. 20 times 3.7. Just straight 74.0 volts. So that would be the nominal pack voltage. So let's just choose this because we like it. But honestly, if you go up or lower, this is similar to like when you buy motors, it'll say the motor rating is a 72 volt motor rating. So you can buy a 72 volt motor. By the way, fun fact, you can run a 72 volt motor. No, it's the other way. You can run a 48 volt motor at 72 volts. That's usually not a problem, and it's a little, I can go in depth why, but I won't do that right now. So you can run a 48 volt motor at 72 volt battery pack, and you're okay as long as you're not going too high, because then eventually the insulation around the wires in the motor could not insulate the higher voltage. But you do not want to take a 72 volt motor and run it at 48 volts. That direction, a higher voltage rating motor run at a lower pack voltage. That means you're increasing the current for the same amount of power through the motor, and you burn it up. I've seen at least 5 to 10 motors blow up because they took a 72 volt motor and put it with a 48 volt pack. But in any case, I guess that's maybe why you want to choose a 74 volt pack, because you can use a 72 volt motor or you can use a 48 volt motor. Maybe that's a good reason to do it. But in any case, let's go ahead and choose 20S as our configuration on the series side. Now, simple math here, guys. If we're going to have, here's like what it looks like when you have series configuration. You've got a little cylindrical cell, and then another one, and then another one, then another one. Then you got your top one. And right here is 0 volts. Right here is 3.7 volts. Right here is 7.4 volts. And then hopefully on the very top, you've got your 20th cell, and it is 74 volts when you get to the very, very top. So that's literally what the battery pack is going to look like. So you can make a 20S pack with 20 cells. And what that means is it's a 20S 1P pack. But how many cells does this have? This only has 20 cells. 20 cells. And how much energy was in each one of these cells? It was 7.4. 20 times 7.4 is 148 watt hours. 148 watt hours. Not even close to the 3200 that we want. In fact, we'd take 50 watt hours a lap. This size pack would only get us 3 laps. So we know that we need more cells, but of course we need more cells. We already decided we need 433 cells. So we know we're gonna do 20S configuration. Let's go over here. Oops, sorry. So we 433 cells divided by 20S. 433 divided by 20 is equal to 21.65, so we'll round up and make it 22 cells. Okay, so now what we just figured out here is how many parallel cells we want. And a parallel cell is one that's literally put next to, so now we've got a 2P. You've got 20S, and now we've got 2P. Well, let's do it again. Now we've got 3P. So you guys following me? You're building the width. And this is when you build the 22 parallel cells right here, 22 parallel cells right here, that still only has 3.7 volts, but it has a lot of amp hours. It has, what did we say? Each cell is 2 amp hours. Where is it? Right here. 2 times 22 amp hours is equal to 44 amp hours. So you have 44 amp hours here and 3.7 volts because this little bottom brick is 1S 22P. And then you do another brick on top of it, which would make the whole thing up to here 2S 22P. And then you go right here, and then you've got 3S 22P. And then eventually you'll get up to 20S, and all of them will have 22P across. So now we've gotten to a 20S 22P pack. And how many cells does this have? This has 440 cells, 22 times 20. And we know that that's good. Okay, well, how much voltage does this have? It has 3.7 volts times 20 is equal to 74. We already decided that. We're just kind of doing a sanity check here. So 74 volts. Well, finally, what is the amp hour? Well, we just did it. 22 times 2 amp hour is equal to 44. So 44 amp hour. This right here are the specs of your battery pack that you are proposing. But we've only done an analysis on the energy side. We know that this could finish the race, but will it finish it competitively? Because we have not talked about whether it will be competitive. Once again, I wish we were looking at a data sheet in order to look at this, but I guess this first one we're just kind of doing theory. So let's do, we know that we're 20S22P. Well, now you have to look at the cell and you have to say, what is the power rating of the cell? Now the data sheet may say it's C rating, but it may also just say the continuous discharge and burst discharge. So let's say one cell it has 2 ratings. Let's say it can do, let me think. 10C on a 2 amp hour would be 20 amps. Let's say it can do 20 amps. Let's say continuous. That's pretty good. 20 amps continuous. But let's say it can do like 30 amp burst meaning like intervals, short intervals of the 30 amp. And that's per cell, guys. That's per cell. And if we know we have a 2 amp hour cell, we know that 20 divided by 2 is equal to 10C. So that's a 10C continuous rating on that cell. And then 30 divided by 2 is equal to 15C burst. So this is the power rating of the cell, just in theory. We're not looking at a data sheet here. So let's go ahead and we took it to C rating, but I guess we'll just work with these numbers right here in here. So pop quiz, do we take 20 amps times the 20 series cell, or do we take 20 amps times the 22 parallel cells in order to find the full pack rate, current rating here based on the cell? You take the cell data sheet and then you can figure out the full pack current rating. Well, it's going to be the P. It's not going to be the S. The S multiplies the 3.7 volts. The P multiplies everything that is current, anything that is amps or amp hour. So remember we said it's 2 amp hour right here. We said these cells are 2 amp hour times 22P gets you the 44 amp hour. Well, in a similar fashion, you're going to take the 20 amps times 22P and you've got 440 amps continuous out of this pack. Okay? And you could have worked this another direction. You could have said, well, this is a 10C. 10C well, there's other ways to work this using the C. If you were given that instead, you would have gotten, 10C of a 44 amp hour pack. That's what you could have done. You could have done, C is equal to amps times amp hour. That means, fill it in. You've got 10C and you've got 44 amp hour and you've got X right here. Solve for X. You've got X equals 440 amps. So in the same fashion, but using pack amp hours and C rating for the cells, you were able to get the same math right here, 440 amps. So 440 amps is your rating on continuous. You could take 15C times 440 and you get the burst, but we'll just talk about continuous. Okay, now we've got amps, but what is the power of that? The power, once again, is equal to I times V, PIV. So it would be the 440 times the pack voltage. We're on the pack level now, and the pack voltage is 74. 440 times 74 is equal to that's really high. Is that what am I thinking about this right? 400 amps times voltage. Oh, 32 kilowatts. Yeah, okay, that is right. 32,560 watts, or this is, 32 kilowatts. Well, this is darn fast. And I guess I have not told you the power for the race. I told you the energy for the race. First we said this, but that would have been 0. Then we said, let's design to this. I haven't told you about the power. Well, I can tell you that the race rules limit, right now, we may update it, but EV Grand Prix limit it to 14 kilowatts, right? 14 kilowatts. So you've just designed a pack that can do 32 kilowatts and we can only use 14. Well, what that means is the cells you use, somewhere in our math, you want to change it to be more on that 14 side, because we probably have, we've overcompensated for the power. We can probably reduce the amount of cells in the pack in order to get a lower number here. What that does is that saves on cost and it saves on weight and volume, but mostly cost. That's usually the biggest thing. So in any case, you can tell that we used power cells. We liked the energy of 2 amp hour. Where is it? Of 2 amp hour. That got us a good amount of energy. But based on the data sheet, the fake imaginary data sheet, we said these can do 10C and 15C. We would want to choose another cell. So I'll go quicker through this whole process, but we're going to do it with a different cell because this is way too different. So that was a 2 amp hour cell and 15C to 10C. That's a power cell because it was such a high C rating and such a low amp hour. Well, let's go ahead and choose a cell that is, in theory, 3 amp hour. Once again, I wish we were looking at data sheets. You can go look at them. And let's say this thing can do more of like a 5C continuous. That seems like something that's reasonable. If you're going 5C continuous, that's 5 times 3 would be 15 amps. And it's still actually, we just did our math on 20, but we're going to have less cells actually. So that we're going to try this out because we will not need as many cells because now we've got 3 amp hour. So let's go through this whole thing again with a cell that looks like this. Well, real quickly, we said we needed an energy of 3,200. Oh, and also let's give the math. What's the power of the cell? Energy of the cell. 3 amp hour times 3.7 volts. 3.7 times 3 amp hour is 11.1 watt hours. Okay, so that is the energy of the cell. We have this much energy needed in the pack. We already decided that, divided by the 11.1, and that equals divided by 11.1. 288 cells. So that's what we need to do. Let's go ahead and use the same 20S configuration. So we're going to do 288 cells. Oh, there we go. 288 cells divided by the 20S configuration, and that equals 14.4 cells. So we'll maybe just round up to 15p. 14.4, so we'll just round it to 15 parallel cells. So we said 20S, and we just found out for 288 cells it'd be 50. So now we just made a 20S 15P battery pack, okay? Let's test out the specs of this with these kind of cells to see if it matches what we like. We know that this is going to be, based on before, 74 volts. We know that, well, here's what we had before. Well, we also know it's going to be 15 times 20, that's going to be 300 cells, which means 300 times the 11.1 is 300, which is equal to 330 watt hours, or 3.33 kilowatt hours. Okay, that's a pretty good kilowatt hours, because remember we said we wanted this much. So we like the voltage, we like the energy on board. What else did we find here? The amp hours. What's the amp hours of this bad boy? We said each cell is 3 amp hours. Do we take the 3 times 20, or do we take it times 15? Okay, it's the 15. So 3 times 15 is equal to 45 amp hours. Okay, now we have the pack amp hours. What does that mean? If we said this can do 5C continuous, you do 5C times 45 amp hours, and that equals 225 amps. So we know that this bad boy is 72 volts, can do 225 amps continuous, has 3.33 kilowatt hours on board, which equals 45 amp hours. Let's do this math and see if we like the energy. Or excuse me, we like the energy, we know that. Do we like the power? Well, what is power? Power is equal to current times voltage. So we have current of 225 amps times 74 volts on the pack level, and that equals 16.65. I really like this, guys. 16.65 kilowatts. Didn't I just tell you that the race was limited to 4? So this is, a little overpower, but let's say they change the rules in the future and we can go up to 16. And this is continuous as well. So maybe it is a little, because this is more of a peak power rating and this is a continuous power rating. So I don't know. I'm just giving a feeling that it could probably do double bursts. It could probably do 10C bursts. So double that would actually be more bursts of like 30 kilowatts, excuse me, not hours, 30 kilowatts. But in any case, this thing can do 16, almost 17 kilowatts continuous, probably bursts from 20 to 30 if you didn't have this limit here. But I really like the power of this pack. I like the energy because the energy will still have a little bit in the pack when the race is over, so we're not really slowing down at the end. We've got good power. So here's your conclusion, guys. We just ran through all the math, got the specs of the battery pack, and we know we want to use this cell. Now, if we looked at the data sheet, we would know the name of the cell. We would know exactly what to buy, where to buy it, the 18650. We want this cell, and we want a pack that is 20S 15P because it gives us the 74 volts. It gives us 225 amp continuous. It gives us 3.33 kilowatt hours. And this is perfect with these cells, this configuration, to race, a 50 lap race at EV Grand Prix with this power limit. So that I think covers everything I wanted to tell you in terms of battery pack design. Just in a quick review, whenever you're thinking of these packs, remember, picture it this way. You're stacking on top of each other for series cells to add voltage, literally stacking on top. And then you're going next to each other for parallel cells to get parallel. You're not adding voltages when you go this direction. You're adding your amp hours when you go this direction. So eventually you go up and you go over, and then you eventually get to something that is 20S, 22P, or whatever your configuration of your battery pack is. Don't forget about C rating. That's really important. Don't forget about the difference between energy and power. Energy is your kilowatt hours or watt hours, and power is your C rating, or it could be your amps times the voltage of your pack, measured in kilowatts. So energy is kilowatt hours. Energy is kilowatt hours. Power is kilowatts. Very important distinction. Okay, guys. Well, I think that covers everything. Thanks for watching. I guess put a comment below if you have any questions. Hey guys, one more thing I forgot to mention when I was reviewing the video. I haven't mentioned this. If we go all the way back to the fact that 3.7 is the nominal voltage for a cell, but I talked about there's a full cell voltage and a minimum cell voltage. Well, that equates to the full pack voltage and the full, zero or the fully discharged voltage. So let's talk about that real quick. If we have 20 series cells, that equals 74.0 volt nominal, but we actually, so that's 3.7, but it's actually 4.2 volts, and you can find that in the data sheet. Sometimes it's a little higher, a little lower, but mostly it's 4.2 times 20S is equal to your, what is that, 84 volts? 84 volt? No, not max. That's full charge. When it's 100%, 100% SOC, state of charge, would be 84 volts, fully charged. But it's 2.8 volts times 20 is going to be your 56.0 volts, fully discharged, or 0% SOC. So this pack ranges between 56 volts when it's discharged, 84 volts when it's fully charged, 74 volt nominal for this pack that we designed. And really quickly, in review, why we did not do 2.5 kilowatt hours and why we instead did 3.2 kilowatt hours is because let's say we're getting towards the end. Let's say, 74 is our 50% state of charge, roughly. Well, let's say we're sitting at 74. Let's say we're sitting at maybe 70 volts. If we have a 70 volt pack, that roughly, it's not linear, but kind of linear, in the middle, at least it is. Let's say that's like 35% state of charge. Well, if we try to pull, how much was our amps? 225 amps. From this, there's something called voltage sag. And if you're using lead acid or an inferior lithium, the voltage sag is going to be worse. So if I pulled just a couple amps from this pack, like 0.1 C, this voltage sag is only going to drop to like maybe 69.5 volts. Well, if I pull 225 amps from it, this is going to drop to like 65 volts only during the discharge. As soon as you stop pulling and stop accelerating the cart, stop pulling the 225, it'll go back up to 70. So this difference, delta V, is called voltage sag. And you need a design for that because when you pull a lot of current from a pack, the voltage is going to sag. Now, this is why, imagine we're getting to 10% left on voltage. Let's say we're sitting at like 60 volts. Yeah, maybe this is more like 40%. If we're sitting at 60 volts and we try to pull 225 amps, it's going to want to dip below 56. It's going to want to dip to like 52 volts. And now you're damaging the cell. So simply put, you cannot pull the normal, like what the amount of power and the amount of amps you could pull from a pack during full charge, during medium state of charge, is not near how much you can pull at the end. You can only pull very, very little amount from a pack near its end because of this voltage sag, and you're really damaging the cells at this point. Cells don't like to be fully discharged or fully charged. So voltage sag is important. It's worse with lead acid batteries. Oh, and by the way, fun fact, if you want to know what's called the internal resistance of a cell, these are usually at the cell level, and it changes. A good cell will be like 0.001 ohms or 1 milliohm. It's like that's ohm, but it would be 1 milliohm would be 0.001. Like the internal resistance of a cell. Well, when cells get damaged, you abuse them, you take them below 2.8 volts, they'll go up. They'll be damaged. The chemistry in them will change, and they'll go up to 0.05. It'll go to 5, 10, 20 milliohms. Well, we know that V is equal to IR, and we know delta V is equal to IR, delta V being the voltage sag, and this being internal resistance. This being current, not to be confused with internal resistance. This is current. This is your internal resistance right here. So if you've got a good cell, well, let's say, the more internal resistance increases the voltage sag. The more internal resistance, this R of a cell, the more the cell and therefore the pack voltage is going to drop when current is pulled from it. So this is the application of what's happening with voltage sag. When you pull 225 amps from the pack, each series cell has internal resistance, and it will add up to equal the delta V, the voltage sag. And as your cells get more abused and get damaged over time, they will increase their internal resistance and have higher and higher voltage sags. And that's why when you eventually come to the end of a battery pack's life, it looks like it doesn't have much capacity anymore. Well, in application, that's because whenever you draw a little bit of current from it, it's going to drop from 84 potentially down to 56 really, really, really quickly, because it's got super high internal resistance, and even just that voltage sag drops it down to the minimum voltage. And most BMS or state of charge calculators will, once you hit this low number, it's going to say, oh, I'm done. Just turn me off or show me a 0% state of charge. So I hope that makes sense. I wanted you guys to know, full pack voltage, under or fully discharged voltage, nominal, and then what it means to have voltage sag and how to account for that and how to measure it too using internal resistance of the cells.